Chapter 28 is about quantum physics, and so we're looking at things that are quantized, and quantized means things are broken up into chunks. And the first case we look at of this is light. Now, we've spoken about light as a wave. In chapter 17, we looked at optics of waves because light is an electromagnetic wave. But there's another way that you can think about it. And experiments in the late 1800s and the early 1900s showed that you could also think of light as a photon, as a particle. And there were some very, very compelling experiments having to do with the photoelectric effect that showed that you could also think about light as having a particle nature. You could think about it as existing in the form of photons. And individual photons have an energy that is determined by the frequency of the photons. And this is one of the first important equations you see in chapter 28, is the equation for the energy of a photon. So when you have a beam of light, and I've got this laser beam right here, I've got this laser beam, it's made up of electromagnetic waves, or I can also think of it as being made up of photons. There's particles of light that come out of here. And so it comes in a quantized form. It comes in chunks of a certain size. And we have the relationship for the energy of a photon. Now I've got two laser pointers. I've got one that's red, and I've got one that's violet. And the brightness of the two is about the same. But now I want to think about not the total power of the beam, but I want to think about the energy of the individual photons, the particles that we can think of as making up these beams. So light has this particle nature. I've got a red laser, I have a violet laser, long wavelength, short wavelength. Question: which one of these lasers emits photons with higher energy? We'll give you some choices. Well, in fact, if I have long wavelength, I have low frequency. If I have short wavelength, I have high frequency, because we have an equation that relates the wavelength and the frequency for electromagnetic waves. So we're thinking about light as a wave, but once we've done that, now we can think about light as being made up of photons, and high frequency, which is violet, corresponds to higher photon energy. And the energy of an individual photon of this violet laser pointer is significantly greater than the energy of the red laser pointer. And we can see that this way. If I take this glow-in-the-dark basketball and I shine a red laser pointer on it, what happens is nothing. And it turns out there's plenty of intensity, there's plenty of energy coming into the basketball, but it's made up of photons, and the photons aren't energetic enough to cause a transition at an atomic level. But for the violet laser pointer, it's a very different story. And for the violet laser pointer, the individual photons have high enough energy to be able to cause a transition. And I can energize this basketball and cause it to glow. And so these photons have higher energy, and it's their higher energy that allows them to do this. Now, if you go beyond the violet into the ultraviolet region of the spectrum, the energy is even higher. And the energy of ultraviolet photons is high enough that it can cause damage to your skin. It can cause damage to biological tissues. And that's why people have sunscreen. And the sunscreen absorbs the ultraviolet light. In the visible light spectrum, you can't tell that. But in the ultraviolet part of the spectrum, the picture looks very, very different. And the reason the sunscreen absorbs the ultraviolet is so that it doesn't penetrate the skin and cause damage, because the photon energies are high enough that that is a very real possibility. So this is the first part of our story. Light, which we've thought of as a wave, has a particle nature. But things that we've thought of as particles have a wave nature. That's the second part of the story, and we'll talk about that in the next segment.